Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll look at correlation and regression. So what we're looking at here is a linear relationship between two variables, x and y. So by convention, x is always the independent variable and y the dependent variable. We're going to try and find a linear equation linking them and see how we can tell whether or not that's a good estimation of the model. So in correlation and regression, we're looking at prediction rather than causation. If there is a linear relationship between x and y, it doesn't mean that x causes y, it just allows us to predict a y value when we know the x value. So we're looking here at scatter plots like this. We have an x value, the independent variable along here, dependent variable along here, and each of these points has an x value and a y value. So basically, if we have a plot of points like this, we're seeing if we can draw a line basically through the middle and how good that line captures the data. So I just made up an example of hours of study and exam result. So we expect that there is a relationship between these two. In this case, hours of study would be the independent variable, exam result the dependent variable. It doesn't mean that this one causes the other. Of course, some people do well on exams without studying. Some people study a lot and don't do so well. So we're not looking at causation here. What we're going to do is look at how we come up with the equation of this line. So we use the least squares method. So if I have a line, let's say this was the line of best fit for this data. You can see though there are errors. You can see there are all these points that don't lie on the line. So this point here, for example, doesn't lie on the line. So we call this distance that it's off by, that's called an error or residual, and there is one for all of these points. So what the least squares method does is it finds the line such that the sum of the squares of each of these vertical distances is minimized. So how good the line is determined by the correlation coefficient, which we call R. So if R is approximately 1 or close to -1, then the data pretty much lies in a straight line. So the positive versus negative is whether the relationship or the gradient is positive or negative. Of course, positive gradient means as one goes up, the other goes up, and a negative gradient means as the independent variable increases, the dependent one decreases. So down here, we'd see a correlation of about 0.5. So, it's kind of lies in a straight line, but not that much. And if the correlation's close to 0, you just get a random scattering of points. These don't lie in a straight line at all. So the way we calculate R, the correlation coefficient, is we find the covariance of x and y and divide by the product of their standard deviations. So let's look at these values here. Let's say x is the hours of study and y the exam result. We'll start by calculating the covariance. So we need a table like this, and what we do is we calculate the distance of each score from the mean. So I already calculated the mean of the x values is 3. So the distance of 0 from 3, that is -3. 0 minus 3, and then 2 minus 3, and then 3 minus 3, and 7 minus 3. We're now going to do it for the y values. I calculated the mean of the y values as 81. So this one is 7 below the mean. The next one is 1 above the mean, 9 below the mean, and then we have this one 15 above the mean. So to calculate the covariance, we need to take now the product of each of these pairs. So I obtained each of these numbers by multiplying these together. So to find the covariance of x and y, what I do is add up each of these numbers. So I get 80, and you divide by n minus 1. So there are 4 scores, 4 observations, so n is 4, n minus 1 is 3. So to find R, we take our covariance, so 80 divided 3 is 26.6 recurring, and we divide it by the product of the standard deviations. I calculated these earlier. So putting that on our calculator, we get that R is about 0.832. So remember that R can only be between -1 and 1, so that one's kind of strong. But R squared is what we really want. It's called the coefficient of determination. So if R is 0.832, R squared is just that squared, and that's approximately 0.69. So the way that we interpret R squared, it's the proportion of variance in the dependent variable explained by the variance in the independent variable. So basically, the relationship here between X and Y explains 69% of the variance. In terms of our example, that means 69% of the variance in exam result was explained by the variance in hours of study. So that's calculating correlation. Let's now calculate regression, which is the equation of this line. So because we're looking for the equation of a line, it will have the form y equals mx plus b. M is the gradient and b is the y-intercept. This is how you calculate the gradient. So in our previous slide, we found that the correlation coefficient R was about 0.832. We found, or I showed you, that the standard deviation of Y was 10.89. The standard deviation of X was about 2.94. So putting that on our calculator, the value of the gradient is about 3.08. Now remember that this is all about prediction. So the gradient allows us to predict. It predicts the increase in the dependent variable per unit increase in the independent variable. For our example, which was hours of study and exam result, our model is predicting that for each additional hour of study, the exam result will increase by about 3.1 marks. So we've calculated M, but we need to calculate B, the y-intercept of our line. To do that, we take advantage of the fact that the line always passes through this special point that has the mean of X and mean of Y as its coordinates. So on the previous slide, I wrote that the mean of X was 3 and the mean of Y was 81. So we simply substitute this with the gradient into our equation. So the Y value equals M, which we found was 3.08, times the X value plus B. So rearranging this equation, we're really just subtracting 3 times 3.08, which is 9.24. We get that B is about 71.76. Accordingly, our least squares regression equation is y equals mx plus b. Now again, we have to be careful. This was done using only 4 observations, which isn't really good for any sort of statistical test, including a regression. But let's now look at making predictions using this equation. So here was the equation that we found in the previous slides. But notice that in our original data, which was only 4 points, the X values ranged from 0 to 7. We have to keep that in mind when making predictions. So let's say we wanted to predict the Y value when X equals 5. Again, this is just a prediction. So what we would get, y equals 3.08 times 5, I'm just substituting X for 5, plus 71.76. So that gives us an answer of 87.16. That is, our model is predicting that if someone completes 5 hours of study, their exam result will be 87.16. It's just a prediction. Of course, it's not a causal link. It's not a guarantee. But this is an example of interpolation because we've used an x value within the range of values from our data points. Let's see what would happen if we use extrapolation. Let's predict what would happen if, say, x equals 10. Well, according to our equation, the y value would be 3.08 times 10 plus 71.76. And that gives us 102.56. So this is an example of extrapolation. We have to be careful here because 10 is outside the range here, and we seem to have got this absurd result. See, because in our original data, we only had x values from 0 to 7, this equation really is only valid for x values within that range. See, our line has a y-intercept of 71.76. So that's basically what we're predicting someone would score if they did no study. But our line had a positive gradient, so it leans to the right. We've basically found that according to our model, if you do more study, then you will attain a greater result. So we stopped here at 7. That was the largest x value in our data points. We don't know what's going to happen after 7. We don't know if the line's going to continue like that or it's going to get steeper. It could even drop off. There could be a phenomenon whereby if you overstudy, you do poorer in the exam. We just don't know which of these it is, and that's why extrapolation is problematic. That's why we can't be sure if someone does 10 hours of study, if this equation will still apply to them. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.